Okay, so in this video we're going to just briefly try to consider titrating a weak base as our sample with a strong acid, such as 0.1 molar HCl as our titrant. Can we compute the pH along the curve? This problem's different because it's a weak base. We haven't seen one like that before, and we're using that down here as our sample. So we want to try to estimate the pH along the curve. Now, point A is always before titrant is added, so 0 milliliter of titrant drained in. So we don't have any of the HCl yet. Let's just say down here that I've got 25 milliliters of my sample, and it's 0.1 molar methylamine. Can we compute its pH? Here's the structure of methylamine. It's a weak base, and it can react with water to set up an equilibrium in which the base accepts a proton to form methyl ammonium. Remember, the amine, the methylamine, got this lone pair of electrons that can be used to form the new bond to make the methyl ammonium, and we're also going to make hydroxide. So before any titrant has been added, I've just got a weak base in a water-based solution. Why can't I just work my Rice table, saying that some of it's going to be used up? 0.1 minus x is my final expected concentration, and 0, 0 plus x, x, and x is what's going to result. And then of course I'd go to my Kb expression. Kb for methylamine is 4.4 times 10 to the minus fourth. And I would do my very familiar x squared over 0.1 minus x. Solve for x, and that will be my pH, okay? So I'm going to guide you through how to handle this case. I don't necessarily need to solve each one for x, because I think that by this point maybe you can handle that. But this is how we would do it for a weak base solution being titrated with the strong acid. Before any titrant's added, you just got the solution of the weak base. Work your equilibrium Rice table, figure out what quantity of protons are accepted by the weak base, how it changes the hydroxide concentration. If you take the negative log of x, you got your POH, and you can easily solve for pH. It will be a bit basic, okay, because we are creating the OH minus in this case, but that's how you handle it. It's as easy as that, okay? Now, after some titrant has been drained, but before the EQ point, we're going to have a buffer solution, just like we did for the weak acid case. Let's see if we can make sense of this. So if we drain just a few milliliters of the HCl into this receiving vessel, what's going to happen is the methylamine will react with the HCl to make the methyl ammonium ion and some chloride. Okay. Now we could do our bookkeeping through an ICF approach, and if we were actually going to solve for pH, we would in fact do that. Figure out how many moles of everything we've got, okay? But what we would see if we're before the equivalence point is that we're going to run out of the HCl. But we're going to have some of this left that's not been titrated. And we're also going to make some of this. Guess what? We're going to have some of this that remains. We're going to make some of this. We've got a weak acid and its conjugate base. We've got a buffer, don't we? So for this situation, we can use our Henderson-Hasselbalch equation after figuring out how many moles of both of these we've got. Use our Henderson-Hasselbalch equation, solve for the pH using the pKa of this form. Easy as that, okay? I'm just guiding you through this real fast just so you kind of seen it. But if you can work the weak acid example we showed earlier, you should be able to work this one. Now C will be at the equivalence point for this type of titration. So let's see what will be going on there, okay? So at the equivalence point, you're running this reaction. This is our titration reaction. HCl reacts with the methylamine to make the methyl ammonium and some chloride. Now at the equivalence point, you're not going to have any of this left, and you're not going to have any of this left. None of these will be present. However, you will have made some of this. you will have converted all of your initial amine to this form. And that's crucial, because can't that act as a weak acid? Can't CH3NH3 plus donate a proton to make H plus in this case, and CH3NH2? And if I work my Rice table, I could figure out the molarity of this stuff, put the molarity right here, do a minus X, and initial molarity minus X is 0 and a 0, a plus X, a plus X. And then I would have what? X squared over that initial molarity minus X, and that's going to equal my K. And in this case, since I have a weak acid acting as an acid, it's my Ka. So what I'll find is that at my equivalence point for this titration of the weak base with the strong acid, it's actually going to be slightly acidic. And if I wanted to get specific about the numbers, I could. I just have to, fill in the gaps here, so to speak. All right, but it's going to be slightly acidic at the equivalence point for this type of titration. And then lastly, after the EQ point, what's going to be the case there? Well, after the EQ point, I would do my analysis, and I would find that I have a non-zero number of moles HCl, because if I'm past equivalence, I'm going to have some of this remaining. Guess what? That is a direct source of H plus in the solution. So what matters after the equivalence point is just how much extra H plus you've got. So you want to compute the excess concentration or molarity of H plus due to the over titration, and then go right to your pH is equal to negative log of H plus equation. And you're in business, okay? So even if you see an example somewhere, in the homework or whatever, where you titrate a weak base with a strong acid, you can handle it. You take the exact same approach that we did for the weak acid in the strong base case. It's just a little bit in reverse, because now you're titrating the base with the strong acid. So you make the acid form instead of the base form, and things are a little bit flipped. But the major ideas are essentially exactly the same in terms of how to work the problems. So don't let that confuse you.